Hello everyone, my name is Naveen K. I am currently pursuing my PhD under the guidance of Dr. P.V. Manu and Dr. Sanjeev Kumar Manji, Assistant Professor in Mechanical Engineering Department at NIT Calicut. My broad area of research is fuel cell. The different types of fuel cell are available, like proton exchange membrane, methanol fuel cell, and phosphoric acid fuel cell, etc. So I am choosing the proton exchange membrane fuel cell because the proton exchange membrane fuel cell, the reactants are hydrogen oxygen. They will form water, and that water is a byproduct, and it will generate electricity. And the operating temperature is low compared to other types of fuel cell. And I am focusing on optimization of microchannel design in proton exchange membrane fuel cell for enhanced performance and water management in portable system. The problem we are using the proton exchange. The problem is water management. We need to control the water management, otherwise it will reduce the performance of fuel cell. So this is the working of proton exchange membrane fuel cell. Left side is anode and right side is cathode. We know the hydrogen is coming from anode side, and it allow only proton to transfer. The membrane allow only proton to transfer, and the electron is going to the external circuit. And in the cathode side, the oxygen is coming, and the oxygen and the hydrogen is formed and water and produce heat. And this is the working of proton exchange membrane fuel cell. Then why we are using microchannel? The interesting features of microchannel, it offers several advantages thermal and fluid management application. It will provide high heat transfer rate, and it will enabling cooling transfer due to the high heat transfer area, and it will enable cooling due to the large surface area to volume ratio, and it will provide low thermal resistance, ensure an efficient heat transfer and heat dissipation, and it will overall improve the system performance. And the compact structure of microchannel make them it's ideal for miniature and a high performance thermal energy application. Additionally, they require low coolant fluid, and it reduces the pressure drop in the channel and energy consumption in the cooling application. One of the most significant benefit is its ability to maintain a uniform temperature distribution and preventing localized hotspot and ensuring efficient thermal management. This feature make microchannel particularly useful in proton exchange membrane and other advantages in cooling systems. So next is my research progress. I am conducting a numerical study in the parallel flow channel. This figure I mentioned the geometry, and then this is the mesh part, and the top side is considered as the cathode channel, and bottom side is considered as the anode channel, and the membrane is considered as the polymer membrane. It's an aphion, and the cathode gas diffusion anode present in the geometry. Before we need to conduct a numerical study, we consider the assumption, governing equation, and the boundary condition. These are the assumption and boundary condition. And next, we need to get the result from the console. And the first we need to find out the molar concentration of H2. We will apply the hydrogen in bottom side. The what happen if the hydrogen is flows from one side to back side, the one side, inlet to outlet, the diffusions happen. It will reduce the molar concentration because of the diffusion. Same for the oxygen. Oxygen inlet is inlet to outlet. What happen? Diffusion. It will combine with hydrogen, so the molar concentration reduce. The oxygen concentration reduce along the channel. Next is to find out the study about the molar concentration. The H2 is formed in the maybe H2 for theoretically H2 is formed only the cathode side, but actual case it will some amount of it will be come to the back due to the back diffusion. It will come to the anode side. It will reduce the performance and increase the concentration loss. And there are three losses available in the polymer electrolytic membrane, that is ohmic loss and activation loss and concentration loss. And the concentration loss lead to loss lead to the high water concentration in the anode channel is more. The concentration loss predominantly increase. So next, this is the if you are increasing the temperature, operating temperature, what happen to reduce the current density. So we need to find out because the proton exchange membranes will also operate low current and low temperature application, and my future works are binary optimization and due to different types of geometry, and it will validate with, and I need to validate with experimental data. And my expected completion of PhD work is within 4 years. So that's it. Thank you.